All right, everybody. Thanks for coming out. We're here to listen today to Justin, and he's going to teach us all about writing tests for pre-existing code bases. And if you have any questions as he talks, just ask that you kind of hold them, chat with him after. And with that said, let's welcome him onto the stage.
Good afternoon, everybody. Happy to be at PyCon again, all my favorite Pythonistas. So thank you for joining me here, and thanks for coming out to beautiful Cleveland. So this is my talk. What is this mess? That's not referring to my hair. We're going to be talking about writing tests for pre-existing code bases. So quick about me. That's me. You can find me on GitHub under Mr. Name, because that's my name, my real name. And you can see in the picture that I do boast the largest terminal in Southern California. Very much wow. So I'm a back-end engineer at SpinFX Group. We write code that powers crazy contraptions and VR experiences. And I do want to give a quick shout out to them for sponsoring me to come out here. So if you learn anything from my talk, you can thank SpinFX. And if not, you can blame me personally. So pre-existing code is not necessarily what we're here to talk about. We're really talking about legacy code. And so we should just briefly define that. The name would imply that it's old, but that's not the case. There's old code that's not legacy, and there's brand new code that is legacy. Some of us are writing it right now. Don't look at my GitHub. So I would define legacy code for the purposes of our discussion as code that's lacking in tests, either no tests at all or minimal tests, maybe tests that don't even work because they haven't been run for years. Lacking documentation, every kind of documentation, doc strings, comments, even overall user documentation, or code that's just difficult to read or reason about. So if your code base matches one or more of these things, you're dealing with legacy code. So why should we even bother writing tests for legacy code? It's a good question. I'm going to answer it with a better question. Why shouldn't we? And there's a couple of good arguments for that, so I'll go through them briefly for all the contrarians out there. It'll be replaced eventually. Right? Software is not going to live forever. Or will it? It's not going anywhere. Maybe that's not being fair. Maybe it will go away, but it's not going to go away right now. If you think about it, in order for code to become legacy code, it has to be serving a very important business function. Otherwise, it wouldn't be there, and you wouldn't be maintaining it. So nope, it's not going anywhere. It's been working just fine. Right? It's been chugging along for like 20 years. Everything's cool. Has it been working? Legacy code is often going to have poor logging, poor error reporting, so there could be things breaking under the hood that you have no idea about. And in a best-case scenario, if it has been working, do you want to be the one who's going to come along and break it, finally? You don't have time. That's fair, because you don't get paid to write tests. You get paid to write code. The reality is it's going to take you more time and money to deal with these issues in the wild when they break in your production system. And it's going to take you less time and money to work with the code base in the future as you start to get it under test. And the last thing, you're lazy. We're all lazy. That's why we're here. But I have a slightly different definition of lazy. I say that lazy means being too lazy to fight a fire, not being too lazy to write a test. I'd rather take an hour to write a test than 3 hours at 3 in the morning to deal with a problem. And the last problem, why does it have to be you? You're a good person. Why did this get thrown in your lap? There's no good answer for that. Insert generic motivational poster, I don't know, because you're a good person and you're going to do it. So with that, hopefully I've inspired you. And you're ready to start writing tests for your legacy code base. So you walk into the office the next day and you're ready to get the entire code base under test. And you quickly fall into a pit of despair as you realize that your tests will never, ever cover this code base. It's a gigantic thing. You have no idea how most of it works. There are components that you've never even looked at. Where to even start, right? So to bring a little optimism back to ourselves and get us out of that depression, we're going to start with one simple rule, which is you test what you touch, okay? So we're not going to worry about this massive code base. We're just going to deal with the things that we need to touch. And it's going to look like this. We're going to write a test that asserts the current behavior before you touch the code. Don't touch anything until you write the test. And you write a test that's going to assert your new or modify behavior. You let them fail. You do all your code stuffs. Your tests start passing. You profit significantly. If any of you practice test-driven development, which I hope you do when you can, this will look familiar. It's pretty much the same process, but the difference is step one there. With test-driven development, you're writing tests for code that you are going to create, whereas here you're writing tests for code that somebody else has created and you don't understand, you don't know what it's going to do. And the first test is always the hardest test. You might be lucky, and there might be some tests already in the code base that are running. We're going to go for the worst case scenario, and we're going to say that nobody ever bothered to even write a single test. So before you can write your first test, you need to do a little bit of setup, right? So you need to do some research and find the tools that you're going to utilize. So you need to find a good test runner that's going to work for you, it's going to work for your system. You want to make sure that you're using any pre-existing tools for your framework or whatever modules you're utilizing. And if possible, you want to be creating some reusable test scaffolding. So for the purposes of our demo app today, we're going to choose the following tools. We're going to use PyTest for our test runner, just because I like it. We're going to use PyTest Django, which is just add some utilities for integrating PyTest with Django, which our legacy app is a Django app in this case. We're going to use PyTest Socket to disable sockets during our test runs, just in case. If you think I'm being overly paranoid, maybe I am. But we actually don't know what's going to happen when we try to get this code under test, so let's make sure it's not trying to connect to something in the real world. We're going to use PyTest Cov to make code coverage reports later in the talk. And we're going to use a module called Factory Boy, which is going to help us avoid some boilerplate when we're making model instances in our tests. Cool. So in practicality, that looks like this. A test requirements file. You'll notice it's a .in, and they're unpinned. You can use whatever black magic you normally use to create your .txt with pinned versions, pip tools, or whatever. That's what I use, but you can use whatever you want. Or you can just leave them unpinned and live on the edge. And then we've got our test runner configuration here, so we don't need to think too hard about it, but we're basically just telling it where to find the settings for Django, where the tests live, which files have tests in them. The most important one is that last line, the add opts. So we're disabling socket by default because, again, we're paranoid or smart, depending on how you look at it. And so with that, we can jump in, and we're going to do our first assignment here. It's a feature request, so we have to alter the existing functionality of an app. And all that we've been told is that we need to update a model called Quark to conditionally determine the value of a property called magic. The first thing that you want to do in this case is try to get some context around what these things mean. Unfortunately, everyone who knew what this meant has left the company. So you don't know what a quark is or what the magic behind it is, but you do know that the reason you need to make the change is that the company has acquired a new VIP client. It's He-Man. He's trying to rebrand from Master of the Universe to Master of Quarks. So they must be important. So we'll just take that at face value, dive into the code. So we got a Django model here. If you're not familiar with Django or with models, don't worry too much about it. But basically, this just represents an object in the database. And we've got two rows in the database, mystery and name. And then we've got some properties, which are properties that just come out of the class and don't relate to the database. And you can see that's the magic property there. So as of right now, it just returns this hard-coded string, such magic. Cool. So before we can write a test, let's do some scaffolding. So we're going to make a Quark factory. And basically, the purpose of this is just to allow us to make instances of quarks in our tests with some sane defaults without having to configure it over and over. So you see I put that in a file called tests model_factory.py. And that Django model factory is coming from the Factory Boy package. And so we're going to start off with a unit test. Most of you probably know what this is, but in case you don't, unit test, ideally, we want to cover the smallest piece of code that we possibly can. We want it to run fast because we're going to have a lot of them. And if they're too slow, then people won't run them. And ideally, they shouldn't use a database or file I/O, anything like that. Because we're testing models, we do need to at least simulate a database. So we're going to ignore that requirement and just go ahead and do it. Cool. So we can start setting up our test class. So we're using our Quark factory there. And in that setup method, I'm assigning an instance of the quark to self.quark. So every time a test runs, we'll get a fresh one of those. And then we're going to go ahead and write the test for the existing functionality, like we promised we would. So we're just asserting that the quark has a magic property, and it returns such magic. And we run the tests with PyTest, and it passes, which is exactly what we would expect. Now we need to write a test that's going to introduce our change. And so the deal here is that if the name of the quark is He-Man, the magic property should always be incredible magic to differentiate it from inferior quarks. And so in this test, we're just assigning the name of the quark to He-Man, and we're testing that it has the string that we expect. And as we expect, the test will fail, which is good. It's exactly what we want. We get some helpful output on why it fails, even though we know why. So now, at that point, we've got the test scaffolding in place, and we've got a test for the current and the new functionality. That means we can actually finally go ahead and touch code. There we go. So we're just going to do something super naive, because this is the only requirement we have, and we're just going to check the name and return the other string. And your tests are passing, right? You've mastered the code base. And you go home and you celebrate. But when you come into the office the next day, something seems amiss. You see there's a bug report, and He-Man says that the magic property is completely broken now. You don't really know what that means, but when you go look at the bug report, you see this. So you were told to change the model. Well, we didn't ask enough questions, because it wasn't really about the model. It's about the endpoint that He-Man uses to create his quarks. And so he created a quark with the name of He-Man, and it does not say incredible magic, and he is furious. So where did we go wrong? When we're dealing with legacy applications, there's nothing wrong with unit tests, and you want to have them. But in reality, you want to be testing the functionality of a legacy application, because we need to keep in mind that we're dealing with a large system that we don't have a lot of knowledge of. So in this case, we changed the model because we thought that's where the change needed to happen, but we never bothered to test the actual behavior that we should have changed. So that would be more what you'd call integration testing, where we're actually just testing the functionality of the app within the context of how the components are working together. That kind of testing makes He-Man very happy. So let's see what that would look like. This is probably how we should have started, right? If we would have known we were dealing with an endpoint, maybe we would have started here. And so now we're testing the exact same behavior, but we're testing it on the actual view instead, which is good because now we can reproduce the error. And that will give us the confidence to start digging through the code base, at which point you find this. Somebody in the serializer, which sits in between the model and the view, decided to override it and hard code that there. If you want to just go nuclear on that and get rid of it, don't. It's probably there for a reason. I found with legacy code that there's almost always a good reason that something was put there, even if that reason is no longer valid. So determining what to do about that gets a little bit hairy, but we actually don't even have time to worry about that, because somewhere in a dark corner of the office, you hear the cry of Skeletor. So there's an emergency bug that we have to fix right away. So that assignment's going to get shelved. And in assignment 2, we're going to deal with code that touches the world. So we're going to fix a bug in a method that actually has some side effects. So we've got an endpoint here. You give it an array of integers, in this case 2 and 4. And it gives back a new array with crazy sauce on top. This is similar to the quark in the sense that we don't really know what crazy sauce is or it's supposed to imply. But when we look at the return value, we've got old sauce and new sauce, and they seem to be the same. So He-Man noticed that and thinks that old sauce should be 2 and 4, which makes sense. So let's go ahead and start looking through the code. Do not touch, only look. So we've got a little view here, and it looks like it's using another module called crazy sauce, and then it's just passing the request data to it, and it's passing it a 2. We don't know what that is. Just take it at face value, and it's returning the response. So let's get into the crazy sauce, which seems to be the bulk of the logic. And we've got a class here. When it initializes, it makes an instance of smtplib.smtp, and then it's got this make sauce method. It's looping through the things. It's pretty hard to tell what's going on because of the variable names, and we don't really know what things or sauce factor mean. But at least we have kind of a feel about what's happening here. So where can we even start with our testing? Let's just try to get the class into a test harness. That seems like a good place to start, right? Super simple. Let's just try to make an instance of the class. Cool. So PyTest socket, it saved us. When that class gets initialized and it makes that SMTP object, it wants to actually connect to a real SMTP server. So if you had a mail server running locally and you ran this test, we have no idea what it would have done if it had connected successfully and the mail server didn't require authentication. Just bear with me. Theoretically, it could have emailed somebody, we'll say. So we're being careful here, but we get blocked right away. So we can't even make an instance of this thing to test. Where do we go from here? This becomes an issue of what's called breaking dependencies, and it's probably the biggest and most common theme that you will deal with when you're trying to test legacy code. So the problem here is we want to test crazy sauce, but we can't because it wants to connect to a mail server, but we don't want to test that part. We don't care about it at all. We just need to get past it. There's a lot of really clever techniques for breaking dependencies. Luckily in Python, we generally don't need to use them because we have really awesome tooling. So here's one or two approaches that generally works well for me in these situations. The first is subclassing. I could do this in a test. It's inheriting from the real crazy sauce, so it has all the same methods and properties, but I'm just going to override init and assign a mock object to .smtp. And then I can write a test that looks like this. And that, if I run that test, whether it passes or not, it's at least not going to stumble on the SMTP connection. So that's good. We can move forward. But as we talked about, we really want to be testing the view, right? We do want to have unit tests on the class, but we also need to test the overall behavior. So we're going to go ahead and write our view test. And when we try to run that, right, because in the view, it's not using our mocked crazy sauce, it's using the real crazy sauce. So in this situation, this is where mocking and patching becomes very handy. The code sample might look a little bit funny to you because dealing with mocking init is particularly painful. But all we're doing here is that we're saying inside of this particular test, whenever I create a new instance of crazy sauce, run my mock sauce init method, and then return the results of that. So I think there's actually a patch talk going on right now. So if this looks really crazy to you and you're more curious about that, you could maybe run down to the other talk. And so at that point, that's going to let us go ahead and get past the SMTP problem, right? And now we just have a failing test, which is cool. That's exactly what we want. And we have, I think, kind of a good idea of what's going on here at this point. It looks like the data is being actually mutated inside the view, right? So let's go fix things. The first thing we should fix is the doc string on this method. Let's make the world a better place. We figured out kind of what the things are. They're integers. And we kind of figured out what sauce factor is. It's a 2. I don't know why. And so we're going to put some doc strings here that explains what's going on to the best of our knowledge. And we even put a helpful little warning that the input data is going to be mutated. So this is nice because the next person that comes in here is not going to be mystified the way that you were. And it will also make it easier to read, as well as being able to bounce this down to documentation. Keep in mind, too, that adding comments or doc strings is like the safest change you can ever make in code. You're highly unlikely to break things unless you forget a quote or something. Let's go actually fix stuff now. So this is the exact same view. We only changed one thing. We're passing a copy of the old stuff instead of directly passing the variable. So that's cool. The test will start passing. We fix the bug. But you're like, wait, that thing should not be mutating data, right? I agree. It's a terrible idea. You really wouldn't expect it if you're using a method like that it's going to actually mutate what you pass it in place. But the reality in legacy code is we could have broken things that are already using that mutated argument, right? So in the beginning, we were talking about, this thing's been working fine forever. Well, turns out it wasn't. But in the meantime, there are other things that have been dependent upon that. So we should just fix the broken thing, right? We shouldn't try to be too smart for our own good. We're trying to maintain the app. Once we learn more about the app, maybe we can go back and make that change. The time is not right now. Lastly, if subclassing and mocking really can't get you through it, you can end up in this catch-22 where you just can't test the code without changing it, and you can't. We said that we were not going to change the code without a test, but we can't write a test. So what do? In this situation, sometimes it does make sense to change code and make it more testable. But you should only do that if you can do it without breaking the interface. So we need to make sure that everything using this thing can still work. And ideally, you should only do it if it actually makes sense in the real world. So as an example, here's an approach where we could pass SMTP in as an optional argument. This kind of makes sense in the real world too, because maybe we don't want to use the default SMTP object. Maybe we want to pass our own. So that'll make it more testable, and it makes it a little more user-friendly as well. And here's another approach we could take. We could use a property instead, so that only gets called when something tries to use SMTP, not when we instantiate the class. That'll make it easier to mock and to patch. Cool. So we'll move on to assignment 3. This is adding new features to existing and unruly things. So we've got a processor class here. It does a lot of things. It's doing like an HTTP request, doing a whole bunch of stuff with the results, writing to a file. Lots of side effects that we don't want to deal with. And we have an assignment to add extra reporting. We're going to add SMS reporting to it. And the approach we're going to take depends on how much time we actually have in reality. We can't spend forever on this. So let's take a best case scenario where you do have all the time in the world. How are we going to approach it? We can try to mock our way through it, right? There's nothing wrong with that, and mock is there for that reason. And it would look a little something like this. The advantages of that, your existing code is fully tested. You didn't have to change anything. That's awesome. That's our goal. Disadvantage, it can be difficult to implement. As you saw there, we only had 3 mocks. Who knows how many more mocks we would have needed? Like, we might have ended up mocking 15 things to get through that method. And the tests become brittle because they're tied to the actual implementation. So as soon as somebody goes and changes something in the code, you've broken all your test suite, and you don't really know why. We could consider refactoring, right? So like, this looks a little bit cleaner, a little easier to deal with. So, and our tests would be a little bit cleaner if we refactor, right? So the advantage there, our code is easier to read and work with. It's easier to test. Disadvantage here, you might break something, which is exactly what we're trying to avoid by writing all these tests. And technically, that refactoring was not directly required to implement the feature. So it can be difficult to justify the time taken in that and the risk. Okay. Worst case scenario, you don't have any time at all. You need to add the thing. First approach, just write the code in the existing method. Advantages, I was originally going to say none, but I realized there is one. It's just the quickest way to get the job done, technically. Disadvantages, your code is untested. You're highly likely to break something or everything. And you just made the code even worse. So you're making your own future grim. Here's another approach. We can make a new method, call it from the old one. So the advantage there is that we can write a small piece of code and we can test it easily. Disadvantage, we can't test the way that the calling method is using our code because we still have not touched that at all. So we only tested our new little thing that we added. And one last option here is subclassing again. So we could subclass processor and make an SMS processor. And then we can just call the parent class process many things method and then do whatever we need to do with the SMS. Advantage there, we can add functionality without affecting the existing class at all. So there's no chance of breaking the existing class. The tests are better. We can mock super. We can test the way that these things are actually working together with each other. Disadvantage, you kind of just increase the complexity of the code base. If only the SMS processor is going to be used, then you have a class that's kind of sitting around doing nothing. It's going to cause a little confusion. And you have to replace the existing class instances in the code base with your new one. You could potentially make a mistake there. As a summary on that part, which one's right for you, there's really no good answer. I'm just giving you a couple tools. So cool. Are we even making progress? We're putting a lot of work into testing. Is it giving us any kind of benefit? Well, a good way to try to gauge that is to use code coverage reports. So let's see how much we're actually covering in the code base. It's a little bit small, but up at the top, I'm just running pytest space dash dash cov. That's what pytest cov did for us, which is awesome. And then we can just, with a couple commands, we can actually look at the code coverage in a browser, which is cool, because you can drill down into here. So in this example, you can see we have a magic 2 property, and we only tested half of line 25, so we never made it to line 26, and there's a do awesome method that we have not even looked at all in our tests. This is really helpful, and I use it a lot, because sometimes you'll write a test, and you think you're covering something, but you're not. So you want to make sure that you're actually covering all the branches. And where do we go from here? You want to create a legacy for the future. A good kind of legacy, not like legacy code. And so how can we do that? We want to be introducing CI and CD to the process if it's not there already. So at a bare minimum, pushing code should run a build. The build should run tests. The build should fail if the tests fail. And ideally, the build should fail if your test coverage drops either by a certain percentage or like below a hard limit. This keeps people honest when they're dealing with the code. So nobody's changing something without a test. And if they do, then it'll become obvious. And keep testing. So we've gone with the philosophy of test what we touch. But eventually, we're going to move beyond that. So just start testing things you don't need to test. It sounds simple, but it's kind of not. You might want to take a test sprint. If you guys have an extra day in your schedule, then you might want to just put a day aside for the whole team to work on tests, testing things that may or may not even be used in the code. And I also like to use it to refresh my brain if I'm working on a huge project or something I've been thinking about for too long. Sometimes it's nice to take a couple hours to work on some tests and put a different hat on, kind of refresh your brain a little bit. So with all that, go forth and test things. And I thank you so much for your time today.